Okay, so part of the assignment that you're going to be working on today is going to be involved analyzing some data. And that data is coming from the World Meteorological Organization Global Atmospheric Watch, which is a group that monitors global air quality and analyzes composition of atmospheric gases and particulate matter. This is particles in the air. Normally, we don't see particles in the air, in large part because they're too tiny to see. But an example of when we were able to see particles in the air would be this last summer when the Canadian wildfires were occurring, and that we had days in Milwaukee where it was incredibly hazy. So what you were seeing then was actual particles from the smoke and debris of the Canadian wildfires in the air. You are going to be analyzing 3 graphs. And each graph is looking at a different particle in the air and its concentration or amount of that particle in the air. You're going to be looking at carbon dioxide, methane, and nitrous oxide. And so some of these particles are expressed in something that we call parts per million or parts per billion. And what parts per million means that if we take a sample of a gas, in this case air, that has 1 million parts in it, 1 million particles, we're looking at the number of, let's say, carbon dioxide particles that are in that 1 million particle sample. It would be like if I was making salt water and I had a 1 liter container of salt water, and so I had like 4 or 5 of them. So if I was like 1, 2, 3, 4, 5 containers that each had 1 liter of water in them, and if I put 6 grams of salt in, and 7 grams, and 10 grams, and 13 grams, and 100 grams of salt into that container, it would be the amount of salt in the amount of water. And that's what the parts per million or parts per billion means. And so these samples were taken in Australia, and the data was taken over the last 40 years. So I'm going to take some time right now to show you how to analyze the data for part of what you're going to have to do today. So the first one that we're going to look at is carbon dioxide. So we are going to be analyzing data for the decade for carbon dioxide from 1980 to 1989. And so if you look at the graph right here, what you can see is that we have the years, the decades of 80, 90, 2000, 2010, and 2017. And then we have parts per million that appear to go by tens up the y-axis. And we need to identify the data that's associated with 1980 and 1989. So I'm going to use a ruler. You don't necessarily have to, but this is how I'm going to do it. So I'm going to go ahead and I'm going to draw a line at 1980, and then I'm going to draw a line where 1980 intersected the graph, which looks something like this. Now, at this point, when I read this data, it looks like that it's somewhere between 330 and 340. So I'm going to estimate that it's about, I don't know, let's say 300, and it's a little bit more than 335. So I'm going to say it's like 300 and like say 36. Okay, so it's 336 parts per million. I'm then going to look at 1989. So 1990 is here. I'm going to estimate that 1989 is like right here. So I'm going to go up and I'm going to go over, and it's just below that 350 mark. So I'm going to go all the way across this way, and I'm going to estimate that it's probably about 349 parts per million. So now what I need to do is I need to analyze the data so that I can get the percent increase, because that's what I have to calculate. So I'm going to do that by, first of all, finding the difference. Okay, and so I'm going to take the year 1989 minus the year 1980. And that means that I'm going to take the 349 minus the 336. And when I do that, I get a difference of, let's see, what is that, a 313, it looks like. And so that's the first step that I'm going to do. The next step that I'm going to do is I'm going to calculate, or I'm going to divide the difference by the 1980 value. And I apologize for that long pause, but the calculator that I grabbed, I misplaced, so I had to go grab another one. So the next step that we're going to do is we are going to divide the difference by the 1980 value. So if the 1980 value is 336 parts per million, I'm going to take the difference, which is 13, and I'm going to divide it by the 1980 value, which is 336. And when I plug that into my calculator, I'm going to take 13 divided by 336. And that's going to give me a value of 0.038. I'm going to go to 4 decimal places, so it's 6, so I'm going to round that to 7. And then the third step that I'm going to have to do here is I'm going to calculate the percent increase. And I'm going to do that by taking this value here and multiplying it by 100. So 0.0387 times 100. So I'm going to do that on my calculator. 0.0387 times 100. And I'm going to get a percentage increase of 3.8. We're going to round that to 3.9%. So for this decade right here, the percent increase is 3.9%, and it's a plus percent increase. So now I've done that for carbon dioxide, and I need to do the exact same set of calculations for the next graph, which in this case is methane. And you're going to notice again that it's the decades 1980, 1990, 2000, 2010, 2017. You're going to have data that does this weird up and down thing, but regardless is we're still doing the same thing. So the first thing I have to do is I'm going to grab a ruler or straight edge, or I don't even have to. I can just simply kind of eyeball it. And what I'm going to do is I'm going to take and draw a line up where the graph intersects, and I'm going to go across. And in this case, it looks like it intersects at 1,500. So in 1980, the number of particles of methane that was in the air in parts per billion is 1,550. I'm then going to go ahead and locate 1989, and I'm just going to kind of be consistent. So I'm going to use this number that's right in front of here, and I'm going to go up and over. And it looks like this one intersects right about here. So when I go back, it looks like it's 1650, 1700. So these appear to go by 50s. So it looks like it's kind of in the middle. So I'm going to say 1650, 700. What's half of that would be, I don't know, let's say 1675 maybe. So we're going to call this 1675. And again, these are parts per billion. And then the math steps are going to be the same. So I'm going to find the difference. So I'm going to take the difference of 1989 minus 1980. In this case, 1989 is 1,675 minus 1980, which is 1,550. And when I subtract that out, I get 1,675 minus 1,550, and I get a value here of 125. I'm going to divide the difference by the 1980 value. So the 1980 value here is still 1,550. So I'm going to divide that difference, which is 125, divided by the 1980 value, which was 1,550. And when I divide that out, I'm going to get 1,125 divided by 1,550. And I'm going to get 125 divided by 1,550. And I'm going to get 0.0806. Leave it at that. And now I'm going to calculate my percent increase. So again, I'm going to take this value, 0.0806. I'm going to multiply it times 100. So I'm going to take 0.0806 times 100, and I'm going to get about 8 point, let's say 1 So in this decade, we have a plus 8.1% increase. And we now need to do the same bit for nitrous oxide. So we're going to do the same process. I'm going to grab my ruler and start at 1980. I'm going to go up and over. So it looks something like this. And where the line intersects, I'm going to go across and see that that's roughly, it's at 305. So it looks like it goes up by ones. It looks like it's just above 300. So I'm going to say in 1980, the value of nitrous oxide was 301, and that's parts per billion. And for 1989, I'm going to do the same process. So I'm going to go up, and I'm going to go over. And again, that looks right above. So it looks like it's about here. And so, oops. Okay, so that looks like it's right above 305. So I'm going to say that that looks like it's about 306. So our first step is to calculate the difference or find the difference. So we're going to take the difference of 1989 minus 1980. So that's going to be 1989 is 306. 1980 is 301. When I subtract that out, I get something like 5. We are now going to divide the difference by the 1980 value, and we know that the 1980 value is 301. So the difference is 5 divided by 301. So I'm going to grab my calculator. 5 divided by 301 is 0.0166. So I'm going to go 0.10, nope, 0.1, what was the number? 66. So I'll make that a 666. I forgot the 0. 0.0166. That makes more sense. Yeah. Okay, so now I am going to calculate the percent increase, which means I'm going to take this value, 0.0166, multiply it times 100. And when I plug this into my calculator, I get 1.66%. So it's a plus 1.66% increase, or a 1.7. Let's do 1.7, okay? So we're gonna take this back to 1.7 because we rounded that up. Okay, so we have calculated the percent increase for the decade of 1980 to 1989 for carbon dioxide, for methane, and for nitrous oxide, okay? You have to now calculate that percent difference following these same series of steps for each additional decade. So for carbon dioxide, for example, you would take data that goes from 1990, which is just above that, so it looks like it's right about here, okay? And to 1989, so you do something like this, and then go across like so. And then, so now you have data for 1990 to 1989, and then you can go ahead and do the same process. So you have to do it for each actual decade. So for 2000, we would collect data for 2000. Something like that. And 2009. So it looks something like that. And then we would do 2010. And over. And I know it doesn't look straight, but it kind of is. And then 2017, which goes like so. And so it looks like it's this. It's going to be this little peak right here, which looks like it's right about 400. Okay. So you're going to have to find the percent increase for 1990 and 2000 to 1999, for 2000 and 2009, and for 2010 and 2007 to 2017 for carbon dioxide, for methane, and for nitrous oxide. So because you've done all of the work here, if you follow the steps, when you get to this side here, you can either show the work for each one going across, and I'll kind of demonstrate what that would look like, or you can simply write in your values. So if I was going to show the work for, say, methane going across, so CH4, that would look something like this. I would take 349 minus 336, so 349 minus 336, and that would give me a value of 13. I would then go one step further, and I would take 13 divided by 336 and get 0.0387. And then I would take 0.0387 times 100, and I would get 3.9%. It's an increase. And I can do the same thing for, so that was for, that was not for methane. That was for carbon dioxide. I can do methane now, which is CH4. And so we did the same thing. So we had methane, which was 1675 minus 1550. So we're going to take 1675 minus 1550, and that would get us, according to that would get us a difference of 125. I'm going to take 125 divided by 1550, which according to this data here got us a value of 0.806. And I take that and I multiply that by 100. And I would get a plus 8.1%. And then lastly, for N2O, nitrous oxide, we would take our values that we found, which is 306 minus 301. Which we said was 5. We would then take 5 divided by 301. And according to what we did over here, that was 0.0166. I would take 0.0166 times 100, and I would get a plus 1.7%. So you can either show your work this way and get your answers, or you can show your work this way. And if we look at the back sheet, so this is what this document looks like, and you get to here, and then you get to here, I've got a whole blank space for you to show work back there. So there's a possibility that you could do all of the work back here and just record your answers. Now, the other thing I need to make clear is that we're gonna stop here, okay? We're gonna do the data analysis part together. So I just need you to calculate these things. So your packet that you're gonna get today in class starts with this, and you have to complete this here, okay? And so this is where we have reactant A, which is a baseball bat, and reactant B, which is a baseball, and there's 4 scenarios, and then you have to go into and identify which, based on scenario 1, 2, 3, or 4, whether or not the reaction occurred. And the reaction will occur if a home run is hit. If there's no home run hit, it's considered a failure. And you're looking for collision theory reasoning to support why the reaction occurred or didn't occur. So if you said no, yes, yes, no, right? You have to use collision theory from the notes, which is U5, nope, I lied, U6 and 1, that will help you with that. So this whole packet is due up to here the next time we get together.